Okay, so we know an electron is a subatomic particle that's a part of the atom. But electrons come in more forms than we think, and a lot of electrons come and go in waves. A wave itself has two main parts, its amplitude and its wavelength. Wavelength is actually super important and represented by an upside down Y of some sort. It's measured in nanometers. So using the wavelength, we can solve super fun equations that involve other variables. Those include the frequency of a wave, Planck's constant, and the speed of light. So using these properties, we can solve equations that help determine missing wavelengths or frequencies, and even the energy of the wave. But how, you ask? There are some fun equations to know. The first is simple. C equals wavelength times frequency. C actually stands for constant, and in this case, we're using the speed of light, or 3.00 times 10 to the 8th meters per second. So let's try a simple wavelength equation. Find the wavelength of an electron with a frequency of 2.9 times 10 to the 13 hertz, or 1 per second. Your equation for this would be wavelength equals constant divided by frequency. So plug in all that fun stuff, and you would do 3.00 times 10 to the 8th meters per second divided by 2.9 times 10 to the 13th 1 per second. You would be left over with 1.0345 times 10 to the negative 5th meters. But wavelength is generally in nanometers, so we need to convert from meters to nanometers. There are 1 times 10 to the 9th nanometers in 1 meter, so we need to use this conversion. And there you have it, 1.0 times 10 to the 4th nanometers. These equations are basically plugging and chugging, so you just need to know the formulas and be consistent in the units of measurement.
Another important thing we should know is the electromagnetic spectrum. By finding out the wavelength or frequency of an electron, we can place it somewhere on this spectrum. There are 7 main components of the electromagnetic spectrum. This involves radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays, radio waves being the weakest, gamma rays being the strongest. It's kind of hard to remember these in order, but a weird way to memorize the order is by using friendly mnemonics. Some examples are, rabid monkeys in velvet underpants excrete gummies, or gate X usually lets in most radiation. Yes, they're sort of weird, but unexpectedly effective.
Another important aspect of electrons is electron configuration and orbital diagrams. They kind of go hand in hand. We want to see how many electrons there are and the different levels on which they exist. For this, the periodic table comes in handy. Energy levels are represented by numbers 1 through 7. Sublevels are denoted by the letters S, P, D, and F. This is the order in which they must be filled. This probably just sounds like a bunch of random numbers and letters, so let's try an example. Oxygen is the 8th element of the periodic table. Beginning on the top, 1s, we can count 2 across. On the next level, we begin with 2s and count 2 across. Go over the giant gap and start with 2p and count 4 across. We can conclude that the electron configuration for oxygen is 1s2, 2s2, 2p4, using that information. And with that, we can draw our orbital diagram. Write each level and draw corresponding lines. For every 2 electrons in the original level, put in 1 line. Meaning, in the 3D level, we would draw 5 levels because there are 10 electrons max. So for 1s2, write down 1s and draw 1 line next to it. For 2s2, write down 2s and draw 1 line next to it. For 2p4, write down 2p and draw 3 lines, as a 2p level has 6 electrons max. Now you want to fill in your arrows. For 1s2 and 2s2, you would draw in 1 up arrow and 1 down, each having 2 electrons. But 2p is a little different. There are certain rules we need to follow when doing this stuff, and Hund's rule states that you must fill all the lines with up arrows first before adding any down arrows. Therefore, for 2p4, you would fill in 3 up arrows and 1 down arrow on the first line. And there you have it.
Finally, we need to know about quantum numbers. They seem kind of difficult and confusing, but they make sense when you apply it. There are 4 parts to quantum numbers, and we can actually compare quantum numbers to describing our own locations. I could say that I live in Australia, but to be more specific, I could say I live in Sydney. However, I can still be more specific and tell you that I live on Wallaby Way, and even more specifically, I live in house number 42. Similarly, the location of electrons can be described in 4 levels of specificity. These 4 levels are energy level, sublevel, orbital, and spin number. Energy level is the least specific, while spin number is the most specific. So, most of us know that electrons exist on energy levels around the nucleus of an atom. But did you know that within each energy level there are up to 4 sublevels? and within each sublevel are up to 7 orbitals. Furthermore, each orbital contains 2 electrons. Here's how we name these different parts. Energy level is represented by the letter N. N can equal 1, 2, 3, 4, and so on. Earlier, we said that sublevels are represented by the letters S, P, D, and F, but they can also be represented by numbers. Sublevel is denoted by L. If you take a closer look, 0 equals S, 1 equals P, 2 equals D, and 3 equals F. Orbital is represented by ML, and ML can range from negative L to positive L. Within these orbitals are electrons that can have spin numbers of either positive 1/2 or negative 1/2. It's a lot to take in and you might be a bit confused, so let's look at an example. Let's say we wanted to describe the second unpaired electron in a carbon atom. First, we would have to determine its electron configuration. If we use our trusty periodic table, we'll see that its electron configuration is 1s2, 2s2, 2p2. From here, we can draw our orbital diagram. Now, we want to focus on the last unpaired electron, which, as you can see, is this one. Its energy level is 2, so N equals 2, and it is located in the P sublevel. If you recall, P equals an L number of 1, so L equals 1. Next, to determine its ML number, we have to look at which orbital it is located in. The electron is located in the second orbital, but its ML number does not equal 2. ML can only equal negative L to positive L, and the electron's L number is 1. Therefore, possible ML numbers can be negative 1, 0, or 1. If we call the first orbital negative 1, the second orbital is 0, and the third orbital is 1. Therefore, the electron in question has an L number of 0. But we're not done yet. We still have to define its MS number. As you can see, the arrow is pointing upward. This tells us that the electron has a positive spin number. Therefore, MS equals positive 1/2. And there you have it, everything you need to know about electrons.